classical radiant cavity model. And this work is in collaboration with Prof. Kasadi. Actually, we have worked on this topic for many years, but still we haven't finished it. We have got some numerical simulation results that we think are very interesting. So we decided to share and discuss with you here. And so your comments and your suggestions will be greatly appreciated. Okay, this is the outline for my talk. First of all, I'd like to fill you in with some background. Then I'll introduce our motivations and the model we studied. And after that, from part 3 to part 6, mainly for the numerical simulation results. And the most important issue is to say, in our model, if the system will relax finally to a stationary state, that it's not an equipartition. And we do find that such equilibrium state, it exists, and it has very unexpected scaling invariant properties. And finally, I'll summarize my talk briefly. The black body problem is very famous, classical one. And suppose we have an isolated cavity, and if we suppose that the energy will equipartitioned to all the degree of freedom of both the matter, the wall of the cavity, and the field, electromagnetic modes in the cavity. Then when we conclude that the energy of the wall of the matter will keep flowing into the cavity. And finally, temperature will decrease until the temperature reaches 0. So this is the so-called ultraviolet catastrophe. And of course, quantum mechanics may solve this problem, but it does not mean the classical argument must be correct. For example, we do know, because in the context of a black body problem, the equipartition assumption has never been well justified. So to be precise, we can ask such a question. Following the Newton-Maxwell equations of motion for both the matter and the field, will the system finally reach the equilibrium state and reach the equipartition? Okay. And this question actually seems to be more even difficult than the establishment of quantum mechanics, because it's not until 1972 there is the first work to try to attack this problem. And in this work, actually, the authors suggest a very simplified model, one-dimensional model of the black body problem. It consists of two infinite mirrors put in parallel, and there is an infinite plate, a charged plate at the middle way. The charged plate is allowed to move only in Y and Z plate. This is Y direction, this Y is a point to audience, and this is X direction. Okay, in this model, the authors found that actually it's integrable, and they solved it analytically. And they concluded that, therefore, one never has equipartition of kinetic energy among mechanical and electromagnetic degrees of freedom, because this can be obtained from the analytical solved solutions. This is not surprising because the system is integrable, and we know that an integrable system usually is non-ergodic and do not reach equipartition. At the end of this paper, actually the author suggested in variant of the model. They said we can exert a force there to the charged plate, and the potential is the quartic term, quartic term. And after this paper, this model, nonlinear model, was studied by many authors. And because it's non-integrable, then this study mainly are numerical. And one typical one, I just cite one, is in this paper. And the author found that actually in this model there exists stochastic threshold. Above the threshold, there is a trend towards equipartition for time average among the normal modes of the field. But this occurs in the sense of Boltzmann and Jaynes, namely with a higher frequency requiring longer and longer times in order to be involved in the energy sharing. Okay, this is for many other authors, they agree with more or less the same conclusion. But it was all this work, I mean, were reviewed by. Oh, I'm sorry. Let me mention another one. So for this work, actually, they studied the number of the modes is finite. So in the original black body problem, actually, we have to consider the case when the number of modes tends to infinity. So this problem was studied in this paper. And the author found that even for the number of modes tend to infinity, there is an absence of ultraviolet catastrophe. And they said this is a general property for all the classical field equation of motion whose solutions have analyticity properties. And for a finite mode, they explained why we can observe numerically the equipartition is because in a finite time, the equation of system lose the analyticity properties of the continuous system. So it seems that for a finite system and the infinite system, the properties are exactly different. These works were reviewed by Julio and his collaborators in 1999. Actually, they carefully studied this work and they point out that actually none of those investigations was able to detect a tendency towards energy equipartition among the normal modes of the cavity. Because numerically, it's very hard to see all the trend to the equipartition was conjectured. It's not well evidenced. And for the system, the energy is finite because this energy is conserved. So thus, mechanical nonlinearity becomes less and less effective as energy flows from the matter to the field. This fact prevents the appearance of an altogether chaotic dynamics. So that means as the energy flows into the field, the system becomes more regular. Okay? So they conclude that one therefore needs a model giving rise to chaotic behavior of the mechanical freedoms, no matter how small their energy is. So to introduce the dynamics of chaos to play a role here, and with this consideration, they introduce another model. This is still a variant of the original model. They introduce another plate, but this plate is not charged. So it does not interact with the field, but it collides with the charged plate when the relative distance reaches a given distance. Okay? Then this model is actually non-KM because the sudden collision, the interaction is not smooth, and it's chaotic. It's chaotic. No matter how small the system energy is. So this is very good. And what they found? They do the simulation, and they found that for finite modes, equipartition always happens. This trend is very clear. And if we consider the limits for mode tends to infinity, our results suggest a trend towards equipartition of energy, with the relaxation times of normal modes of the cavity increasing with the mode frequency. And this this conclusion is actually quite similar to the previous study. But here, this analysis is very careful. Actually, the authors here, they produced a scaling analysis. they found that there is some scaling properties. So this trend is actually deduced by a extrapolation from the scaling behavior. So this is much sounder than the previous conjecture. Okay, now let me introduce our motivation. So our original motivation is very simple. Now that for the previous KM system, there isn't a scaling analysis. So we ask whether we can do it, and we can deduce from can find any scaling and deduce the result for the number of modes tends to infinity. So for this purpose, we have to find out if equipartition is reached in a KM system for a given finite n. And if this is yes, then we'll try to find if there are any scaling characteristic. And based on this scaling characteristic, what we can predict. But when we do this, we found a trouble. That is, it's quite possible that a system has a quasi-stationary state in general. So we have to clarify this point first. So these two are our motivations. And we need a new model. And this model, okay, these are what our consideration. First of all, it must be of Km, okay? The second, it must be chaotic in a wide range of energy. So even the energy flows from the field, the system is still chaotic. And this matter accounts for a big portion of energy. It means that when the energy flows, the dynamical behavior does not change qualitatively. And the matter has a higher degree of freedom. This is also from the same consideration. And as simple as possible, our model is. Why? Because the simulation is actually very difficult to do. So as similar as possible, as similar to the previous model as possible, so that we can get some guidance, some help, you know. So then this is our model. We introduce more uncharged plates, but unlike Julius' previous work, we make their interaction smooth, you know, not the collision, but smooth. Okay, this is the topological connection of a plot of our model. The black points here represent the uncharged plates. The dashed line represents the nearest neighboring connection, and the total number of plates is NP. The red one is the charged plate, the first one. And the open dots represent the eigenmode of the two mirrored system. The two mirror system without any plates. Then they have normal modes, and omega is the eigenfrequency. Okay, the total number is n mode. Okay, this is the topological interaction, and this is our Hamiltonian. The first part, this is the kinetic energy of the uncharged particle, and this is a localized interaction, and this is the nearest neighboring interaction, and this is the localized potential of the charged particle, and this is the interaction part. The charged part, only the charged part plate interact with the field modes, and this part is for the modes, for the field modes. This QK is the amplitude of the vector potential along the z direction, and the PK is its conjugate. And for the convenience, okay, let me call this part is still kinetic energy. Of course, it's not, but let me just call this for simplicity, and call this part the potential energy, okay, for the mode. Okay, so now let's choose the interaction of the plates first. We choose a 5-hour plate lattice. Here, we see the localized potential is a quartic potential, and this is a harmonic interaction between neighborings. Okay, this why we choose this one, because this is consider only one plate. It reduces to the original 1972 model. And another important reason is that this system is very complex. Yeah. For example, this is the Lyapunov exponent for the system. We consider here for NP equals 32, and we can see that half of the Lyapunov exponents are positive, okay, for the large range of energy, okay. And this is the largest Lyapunov exponent as a function of the total energy of the system. We can see that from over a range over 3 orders, yeah, last Lyapunov exponent is positive. So this is quite good, and our investigation is in this energy range. Okay. Okay. Now let's see the interaction between the charger plate and the normal mode. This term, okay, and we have 2 parameters. One is epsilon. Epsilon is an overall control parameter of the interaction. It's defined in this way. Sigma is the charge per square area in the charged plate. So this increases as epsilon increases with this guy, and L is the distance between the charged plate to the mirror. Okay, so this is one. Another is AK. AK is a particular interaction between the charger plate with a particular mode. It's AK. AK is given by this formula, and here is Fx. This part is actually the eigenmode, and this part is the how the charge distributed along x direction. Okay, then we usually consider a even function of Fx, and for in the following I will present to you the main results for this one, but it actually qualitative properties of a model does not depend on this particular charge distribution. Okay, I will remind you if I change it to another one. Okay, this is interaction part, and for this particular charge distribution, if we calculate AK, it's a curve like this. It's discrete points. It's not a continuous curve, and we may find that at a certain k value, and AK is very close to 0 here, here, here. And so we can expect that for this mode, actually, the interaction, the exchange of the energy is less effective than others, right? Okay, we also consider the other distribution. For example, this one, a delta function. This one is a property that all AK equals 1. So this one is the most effective one for the energy exchange between the matter and the field. Okay. The last thing is the parameters. Epsilon here and omega k is here. C is the speed of light, and this is k. We can see that actually omega k is proportional to k. So we can identify them. And we set L equals pi, C equals 1, and sigma equals 1. As a result, epsilon equals 2, and omega k equals k plus 1 over 2. Okay? And besides, we consider such a set of setting. We consider 32 plates and 200 modes. But let me stress first that our properties of the does not depend on this particular choice. I will show you later. Okay. Okay. Before I present the data, let me summarize our main results first in order. I cannot finish because we have too many data. The first is numerical simulation results suggested that the existence of a stationary state in this particular model. And this stationary state does not depend on the details of the model and the simulations. We changed a lot of details, but we cannot change the fact that this stationary state. And the second is the stationary state is in clear contrast to equipartition. It's actually a localized one. It suggests a new dynamical localization phenomenon. This is a classical one. In the previous talks, in several days in this conference, we have known that, for example, the localization of breather in FPU model and so on. Then we provide another one. Then the stationary state has a scaling invariant feature. Its underlying mechanism, actually, we don't know yet. So this is what we want to do next, and we want to have some idea from you. And the last one is analytical study maybe is desired, of course, because numerical thing we cannot conclude confirmly. And we find out a simplified model. Maybe it can help. Okay, I'm sorry. Maybe it can help. Okay. I will give you the detail of this model later. Okay, now let me present our simulation results. For our simulations, what we are interested the most is that to see how the energy, if we give it to the metal first, flows to the field. So for this aim, to this end, initially the total energy total is distributed among the plates only. Then the system is evolved to see how the energy is transferred and distributed at a given time, t. Okay, in order to suppress the fluctuations, because all the modes we know it oscillates there. Okay, then a partial average over time is taken. I'm sorry for this. The average is taken for a time period from t to 2t. Okay. For example, if t equals 1,000 from t to 2t. If t equals 1,000, okay, then the average is down between 1,000 and 2,000. Okay, this is what. Oh, I'm sorry. I'm sorry, who can help me? Tell me what. This one. Oh, I'm sorry. Oh, thank you. Okay, let me talk about first the two initial conditions. The first one is that we give all the energy to this guy, the farthest particle, and the second one is all the energy to give the middle plate, and let's see what may happen. And for the simplicity, let me present the results of the energy distribution among the plates first. Then we go to the that among the modes. For the plates, if we look at the kinetic energy, then for the first initial condition, it's something like this. This is for the time 1,000. We can see that still a big portion of the energy is at the original position. And for other plates, they also share a small portion of the energy. And this is for the second initial condition, the same thing, right? Okay. Okay, then let's evolve the system. This is for 10 to 4. And we can see that more and more energy flows to other plates. Okay. And this is for the 10 to 5. It actually, the distribution has lost the message of the initial distribution. Both of them stays at the same thing, at the same place. Okay, this is for 10 to 5. And for 10 to 6, we can see actually the distribution does not change too much, very, very slightly. Okay. Okay, so how about a long time? And this figure shows 10 to 6, 10 to 7, 10 to 8, 10 to 9. And we can say that they do not change too much, very, very close with each other. And this is for the second initial condition, so the same thing. I'm sorry. This is for both the initial condition, the kinetic energy. They are the same. If we look at this is the potential energy between the plates. They are the same as well, also a flat distribution. And this is the potential for the local potential, also the same. These two guys is a bit different because they are the farthest two. Okay. Now let's say what happens for the modes. This is for short time. We divide it into two parts. The first part is kinetic energy, this part. And for the first initial condition, we can see that as time goes by, and actually they converge to the same distribution here. This one for 10 to 5 and one for 10 to 6. It seems that they do not change later. And this is the result for the second initial condition. We have obtained the same thing. The same exactly. And we can locate some dips here. Actually, this one is around 100 and this one 180. And this position is exactly here, what I once mentioned, close to 0 because of a small interaction. Okay, this is a long time result for both the initial condition. Actually, for all other conditions we have tried, we finally get something like this. This is a flat part followed by exponential decay and followed by tail. Okay, and this is the potential energy for the modes. It has the same structure. Okay, if we compare them together, we can see the difference between them is actually very, very small. For this part, they agree with each other. For this part, for the tail, I mean, they have some difference. The reason may be that they are not symmetric exactly because kinetic energy only appears here, but the potential energy appears here and here. It interacts with the plates. Okay, anyway, I mean, the kinetic energy captures all the features of the distribution. Let's come back to make a comparison with the plates, okay? This is the kinetic energy of plates, and this is the kinetic energy of the mode. And we can see that actually they are the same, this part, and then followed by exponential decay and the tail, okay? Because this is a very strong signal that the system has reached a quasi-stationary state. We have to be careful because we don't know if it's stationary or not, and later we'll analyze it. For the FPU model, maybe you know that we find such things, similar things. For a long time, 10 to 3, 10 to 4, 10 to 5, we can find the distribution almost collapse with each other. But 10 to 6, you can see some change. 10 to 7, 10 to 8, and finally reaches equal partition. So we know that for the FPU model, we have the quasi-stationary here. So now let's call this distribution quasi-stationary at this moment. And later, I will just show you the results of the kinetic energy of the mode because it captures all the characteristics of the energy distribution. Okay, to summarize this part, so in our model, a quasi-stationary state is found. It features an energy distribution over the modes with a plateau at a low frequency end, now followed by an exponential decay and a tail sequentially. Okay, this is this part. And this question is very important if it's stationary or not. It could be a quasi-stationary, like what we have observed in FPU model. After a long enough time, and then finally it reaches equal partition. Then the system is equal partition. And it also could be stationary. That means that the energy distribution converges to this guy and does not change at all. Then qualitatively, the property could be completely different. So our strategy to clarify this point is that we investigate the long-time behavior if it changes or not. And we comparing the different initial conditions. If it's, for example, for the FPU model, we have tried this. Initially, it gave the energy to all the modes randomly but uniformly. It will never come back to the stable state. So we also want to try in our model if this is the case or not. And we also check the robustness to perturbations. If this distribution is a final state, we expect that it should be stable. So we can put some perturbation to say if it is still there or not. Now, first thing, just like I have showed you, for a very long time, from 10 to 7 to 10 to 9, this is the longest time we can do. And we can see all the distribution actually collapse. Seems that it stay there, do not change. Okay, then we choose the largest one, 10 to 9, as our benchmark. I mean, I'll use it to compare with the results from other initial condition and from other variation. Okay, then let's see what happens if initially we put the energy uniformly around the system. For a short time, okay, for a short time, this is T to 10 to 3. We can see that it's almost flat, but at the tail, the far tail, it drops. Okay, then increase the time, we can see that it drops further. But when they reach the benchmark here, then they stop the lose energy. If we increase time, then we can find this guy and this guy. And finally, this is 10 to 8, and 10 to 9, they collaborate with our benchmark completely. I didn't plot 10 to 8 because I want to show you this trend. Okay? So this is surprising, and this is the main results we obtain. Even we start from equal partition energy, the system will not stay there, means that actually it's not stable. Okay, this is the first thing. And the second thing is, let's check another initial condition. This condition is that initially we consider only, we gave all the energy to a single mode, the 75th. And what if it happens, see, this is 10 to 4 time. We can see a peak here, and this peak is exactly the initial position of the distribution, and a tail. Okay, this 10 to 4, this is 10 to 5, and this is 10 to 6. We can see that to 10 to 6, the tails begins to form, and this is 10 to 7. It converges to the benchmark greatly, and 10 to 8 it almost overlap. Okay, the same thing. It does not depend on the initial condition. We tried many initial conditions, but get the same thing. Okay, so this suggests that it's actually robust. And another thing is we make a comparison of the integration steps. This the aim is twofold. The first is to see whether our results depend on the simulation details first. The second is to say if the result is robust, because we know the integration steps introduce some round error, and round error plays a role of noise, right? Okay, this is what we found. This result is done by the fourth order Runge-Kutta method, and we choose different integration step. This one, divided by a factor of 2. And actually, we divided it by a factor of 2. The accuracy of integration increased 1 order for this algorithm. And this means, actually, for 3 different orders of accuracy, we get the same thing. This is the result for T to 10.8. We can see them difference here, but the tail and the head, they overlap with very good. This actually is not surprising, because we add some noise, actually we help the system to relax to the final state. This is actually observed by previous authors in their study. We add some noise, help the system to relax. This is also what we observed here. Okay, anyway, this message is that our system is stable. It's robust against distribution. Now let's come back to this figure. So if our system is stationary, now what does it mean? It means that for the plates, for the matter, this is the final state. So finally, the equipartition rate. So if we consider only the matter, it means that the matter is thermalized. It will not change anymore, even you increase it further, integrate it out. So for plates, thermalization at a finite temperature is possible in our model. This is completely different from all previous study. And if so, then we can define temperature of the plates of the matter in this way. Okay, kinetic energy for each plate equals half of kBT. Then we know the temperature of the matter. Then the next question is how this temperature is related to the energy distribution in this area. Okay, now let me summarize this part. The energy distribution of the system converges to a localized, stable distribution as time tends to infinity. The stationary equilibrium state has a semi-equipartition feature. Let me explain. The energy of the matter is equipartitioned, while the energy of field has a plateau exponential decay and a tail structure. Okay, so we call it a semi-equipartition. And the ultraviolet catastrophe does not happen in our model, either for a finite number of modes or when the number tends to infinity. For a finite number, we have seen the result here. For it tends to infinity, I'll show you later, okay, on the next slides. So let me summarize here first. So this result is completely different in clear contrast to previous studies. Okay, now, it's very interesting that in our model, actually, there is an unexpected scaling property. We didn't know where it comes from, but it's very clear. If we study the relation between T, temperature of the plate, and the field energy, E, then what we have is like this. Let's fix the number of plate is 32, and this is what we can say. These three curves for different total energy. We can see that it covers a range of three orders, and all of them have the same structure: platinum, exponential decay, and a tail. Okay, but they do not agree with each other as expected. But if we do such a scaling, we can find all of them overlap with each other, such as scaling. Okay, this is we divided the kinetic energy by T, temperature, and omega K is K plus 1/2 by T sigma with an exponent 0.22. All of them, okay, see, very good agreement. Okay, this is for NP equals 32, and we also tried others. For example, 16. We get the same figure, but if we after do the scaling, actually all of them will fall on the same curve, for the same curve, this plateau and the exponential decay, like in the NP equals 32. And this is the result for NP equals 8. Again, all of them is the same. Okay, this is very strange. We don't know yet. Okay. Okay. This result is for the charge distribution I given you. I mentioned it before, right? It's a hump shape, but for other charge distribution, we also have such kind of a thing. We can scale it, scaling invariant property, but the exponent could be changed. That means the exponent, for example, here, 0.68 and 0.22 depends on the distribution of charge. This is one example. For the uniformly distributed charge, this is the most effective one. Then we can say that still they can rescale, but these parameters changes. Okay, this is what we found. Okay, let me summarize this part. For a given charge distribution, the stationary energy distribution for different total energy and different system size can be rescaled to form a single plateau exponential decay curve. The scaling exponents but depend on the charge distribution. Okay, this is this section. And last, let me answer such a question: how general is it? So I mean, I just mentioned to you our result does not depend qualitatively on the choices of the details of the system and the simulation. But now let me show you the result, what we have tried and what they are. The first thing is that our study do not depend on the total energy. This I have shown because of the scaling behavior. This is another example. The NP equals 32, E total equals 30. I'm sorry, this is wrong. I'm sorry, I made a mistake. This is actually for different energy. They collapse with each other. Finally, they get the same thing. Okay, for in all the energy, I'm sorry, this is actually a different energy. For all the energy, if we check the Lyapunov exponent, all of them are positive. The system is still chaotic. The blue curve is for the system without the field, but the red one is the result for coupling coupled with the field, and only slightly drops, you can see. Okay, so the system is still chaotic in all the energy range we've studied. And our result is independent of NP and N mode. NP we have same, but let me show you the result for different N mode. The same thing, actually. If you increase the mode, actually you increase the tail. This one is for the largest one we tried. You can see it overlaps with the short one exactly. Okay, only have a tail. Please remind it that the energy of the tail actually can be neglected. Very, very small. This is an exponential plot. So this is what I just mentioned. The ultraviolet catastrophe does not happen in our model, either for a finite or even for infinite, because we increase it, we increase the tail, and the energy here is actually, you can calculate it's a finite portion. So our results also independent of the charge distribution qualitatively. For example, this is the delta distribution, and still we can find finally the system relax to this distribution, and we also have the scaling invariant property. And also our problem is actually independent of the linearity of the modes. Our mode is like a harmonic oscillator, but we tried something like this. We put one term, extra term, this is a nonlinear term in the Hamiltonian. We can see if we have the same thing and exactly the same. This is the benchmark, and this is the energy distribution uniformly initial, and we see that converge to the finally to our benchmark. And actually, the result is independent of the motion of the charge plate. We decoupled the charge plate from other plates, but move it randomly. We get the same thing. Consider only the charge plate, then the Hamiltonian of the system reduces to this one. There is only one plate. Okay, but for this one, the system is conserved, the energy conserved, and this model is exactly the model suggested in 1972. But we changed the motion of the charge plate by adding a North-Hoover path. That is, we introduced this term, and this psi changed in this way to keep the charge plate at a given temperature T. Okay. Now this system is dissipative. It does not control the conserve the time, the total energy. So the energy can be pumped out, pumped in from the field. But still, we have saying the same thing. This is initially we give a uniform distribution, and we see how it relaxes. See, finally it relaxes to our benchmark. So it means that this is a general property, does not depend on the details of our model. Let me summarize. Qualitatively, the existence of the stationary distribution as a main feature, semi-equipartition and the plateau exponential decay tail structure in the field is independent of all the details of the system. We have tried everything we can think of. We get the same thing. Okay, now let me summarize my talk. Let's get back to the original question. Following the Newton-Maxwell equation of motion, will equipartition be reached eventually? For our model, okay, our answer is no. Equipartition and ultraviolet catastrophe do not happen. Instead, the system will relax to a semi-equipartition equilibrium state of a finite non-zero matter temperature. Our result is actually in clear contrast to the result of Boltzmann-Jeans equipartition in that sense, because even we increase the time to infinity, our system will do not reach equipartition. Okay, finally, this is the detailed result I've mentioned. Thank you. Yes, I've tried that for the total